Hello students, in this video we are going to discuss about Euclid's division lemma and its applications. Euclid's division lemma has several applications related to finding properties of numbers. Earlier we have seen Euclid's division lemma finding HCF of. Before going learn about the, let us recall definition of given two positive integers and b, then there exists unique integers q and r which satisfies the condition a is equal to bq plus r, where 0 less than or equal to r less than, where r is remainder, q is quotient, p becomes divisor. Let us see one example. So that every positive even integer is of the form 2q, and that every positive odd integer is of the form 2q plus 1, where q is some integer. So we will assume that a be any positive integer, since it is given in our problem b is equal to 2. Whenever b is equal to 2, according to the, we'll write a is equal to 2q plus r. So here you can understand that r is either equal to 0 or r is equal to, because r should be one value, should always be one value less than. So the possible remainders are 0, 1. If r is equal to 0, then the equation becomes a is equal to 2q. If r is equal to 1, then the equation becomes 2q plus 1. Here a is a positive integer and 2q is even integer. You all know that any number is multiplied by 2 or exactly divided by 2 is always even, and its counterpart is odd. So 2q plus 1 is odd. Let us see one more example. Use Euclid's division lemma to show that any positive integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5, where q is some integer. Let a be any positive integer. Just like our previous example, case of b, here we have 6. Divisor is 6. So according to the definition, equation becomes 6q plus r, and the possible remainders of this equation are 0, 1, 2, 3, 4, or let us see, if r is equal to 0, then what happens? A is equal to, r equal to 1, then the equation is 1, r equal to 2 is plus 2, r is 3 is 6q plus 3, r is 4, it is q plus 4, r is 5, it is q plus 5. These are the total possible remainders and values of a. So as asked in the problem that a should be positive odd integer, cannot consider q q plus 2, because can be written as 2 times p into q. Upon taking 2 as common, becomes pq plus 1. Here also by taking 2 as common, q plus. Here we have written this in the form of 2 into some. All these will become even. So cannot consider. Therefore, any odd integer remaining numbers are in the form of odd. It is 6q, 1, 3 and 6. Similarly, we'll see one more example. Use Euclid's division lemma to show that square of any positive integer is of the form 3p or 3p plus 1, where p is some integer. Here, consider a be any positive integer and b is equal to, it should be 9 here, but I considered 3 because 9 into 3 gives 27. Moreover, 3 cube is equal to 27. Anyway, 3 is a multiple of 9. As it is possible in this case, we considered it like this. So, by the definition, we'll get the possible remainders as 0, 1 and 2. So if r is equal to 0, then equation becomes a is equal to 3q plus 0. Since the question is asked to find out the square of integer is in that form or not, we have to definitely square on both sides. Then, as it is a direct one, monomial, directly we'll get the value as a square is equal to some 3 into 3q square, where I substituted this value 3q square with some variable p, where that is equal to 3q square. This is if r is equal to 0. Let us see if r equal to 1, then how the equation. Then it is 3q plus 1 upon squaring on both sides. And here we have two terms. It is a pure binomial. Then we have to use the formula a plus b whole square is equal to a square plus 2ab plus b square. By substituting the terms according to that formula and expansion, we'll get like this. And upon simplification, we have further written like this, and a square is equal to 9q square plus 6q plus 1, and here we can see these two terms, 3 can be taken as common, and I have written this like this, and this one is left over. So a square is equal to 3p plus 1, where this p is substitute for this value, and we'll see the final case where r is equal to 2. If r equal to 2, upon squaring on both sides, applying the same formula a plus b whole square, there will be a little change in the value of the terms. We have 2 here place of 1, a little bit more value we'll have, and this becomes like that, and we have took common 3 from these 3 terms. So you can observe here this 4 is splitted and written as 3 plus 1. This there is possibility, and we can write like that. So from these 3 terms, I took 3 as common. This is 3p plus 1, where this p is written in place of these three terms. Like this way, we took three cases. We have done the possible with all the possible reminders. Finally, we conclude that square of any positive integer is of the form either 3m or 3m plus 1. Let us take some numerical values for this. If I say 6 square, that is equal to 36, and this can be written as 3 into the 12 is, so 6 square is in the form of 3m. Similarly, if I take 7 square, whose value is equal to 49, and we cannot directly cancel 49 by 3, so this can be split and written as 48 plus 1. This can be written as 3 into 16 plus 1, where in place of 16 substitute m. This is in the form of m plus. Similarly, if I take 100, which is 10 square, this also I can split it as 99 plus 1. This is 3 into 33 1. Again, this is in the form of 3m plus 1. Similarly, you can consider any number and its square can be written in the form either 3m or 3m plus 1. That is what it is all about solving this problem. So I hope you understand this problem, and in our next video we'll see about few more examples. I hope this problem and explanation. Thank you for watching.